You are in a dark room. The darkness is not empty. Roughly 85% of all the matter in the universe is invisible, and it is moving through you right now without resistance. Billions of particles passing through your body every second, leaving no trace, no sensation, no sign that they were ever there. We can map this substance. We can weigh it. We can watch it pass through the wreckage of colliding galaxies. We have no idea what it is. And underneath that, older and stranger, sits the question this video is built around. Why is there something rather than nothing? The answer that has been taking shape across a century of physics is not the one anybody expected. It is that absolute nothingness. A true and total void is not a calm absence waiting to be filled. It is unstable. It seethes. It cannot hold. The universe exists because emptiness was never an option. Hello, and welcome to Sidereal. Tonight is about the simplest explanation for why God does not exist, or more precisely, why the oldest argument that a creator must exist has quietly stopped working. If you find this kind of slow exploration useful for sleep, or for winding down, a like or a subscribe genuinely helps the channel, and I am curious where you are listening from. Drop your location and the time in the comments. One question will carry us through the night. How does nothing become everything? By the end, you will understand why the laws of physics may make a universe not merely possible but close to inevitable, and why no hand was required to light the match. The dark matter wind is the right place to begin, because it tells you something about the relationship between what is real and what is visible, and that relationship is the whole subject. We live inside a cosmos where almost all of the matter is undetectable by light. Those particles are threading through your body at this moment, and if you hold perfectly still, you will never feel a single one. They do not interact with your atoms in any way your nerves can register. They pass through the Earth as though the Earth were not there, and yet they are the scaffolding inside which every galaxy formed. The Milky Way sits at the center of a vast halo of this invisible material, a sphere of it extending many times farther than the disk of stars we can see. Without that halo, the galaxy would have come apart long before the Earth had a chance to gather itself out of dust. The iron in your blood and the calcium in your bones were forged in the cores of stars, and those stars ignited inside clumps of dark matter that collected when the universe was very young. You are downstream of something unseen. You always have been. That is the kind of fact this channel exists for, not the spectacular kind, the kind that sits quietly in the room with you afterwards, and it leads directly to the deeper recognition underneath tonight's title, which is that the most fundamental question anyone has ever asked may have an answer that does not require a supernatural agent at any point. I want to be precise about what the title means, because it is a strong claim and precision matters more than provocation. This is not an attempt to disprove the existence of God in every possible sense. Physics cannot do that, and anyone who tells you otherwise is selling something. What tonight does is examine the oldest and most durable argument for a creator, the argument that something cannot come from nothing, and therefore that a first cause is logically required, and ask whether the physics of the last 100 years has shown that argument to rest on a mistake. It has a name and a lineage and a specific author. In 1714, the German philosopher and mathematician Gottfried Wilhelm Leibniz published a short work called Principles of Nature and Grace. He was in his late 60s, near the end of a career that had produced the calculus, a mechanical calculating machine, and a long and increasingly bitter dispute with Isaac Newton over who had thought of what first. In that short work, he wrote the sentence that has never really let go of us. Why is there something rather than nothing? Leibniz was not the first person to ask it, but he gave it the shape that would echo through the next 3 centuries. He reasoned from what he called the principle of sufficient reason, the idea that every fact about the world must have an explanation for why it is so, and not otherwise. Nothing simply is. Everything is for a reason, and if you follow the chain of reasons backwards, one thing explained by the thing before it, you must eventually arrive at a place where the chain either stops or continues forever. If it stops, the last link has no explanation, which violates the principle. If it continues forever, the whole infinite chain still has no explanation for why it exists rather than some other chain. The only way out, Leibniz concluded, is a necessary being, something that contains the reason for its own existence inside itself, that could not have failed to be. That being, he said, is God. It is a clean argument. That is why it has lasted. It does not depend on scripture or on revelation or on any particular tradition. It depends only on the observation that the universe exists and did not have to. Something must have lit the match. It is worth pausing on how unusual that argument is, because it is not a religious argument in origin, and it does not become one until the last line. Everything before the conclusion is a claim about explanation itself, about whether the chain of causes can terminate, and what it would mean if it did. Philosophers call it the cosmological argument, and versions of it long predate Leibniz. Aristotle reasoned toward an unmoved mover, a thing that causes motion without being moved by anything. Ibn Sina, writing in Persia around the year 1000, distinguished between things that are merely possible and a being whose existence is necessary. Thomas Aquinas set out 3 separate versions of it in the 13th century. What Leibniz added was rigor and a name, and what makes his version durable is that it does not require you to believe anything in advance. You are asked to accept only that things have explanations, which seems close to the minimum requirement for thinking at all. Nearly every human culture has produced a version of this story. In many of them, a god speaks or breathes or dreams the world out of a formless void, and the void is always the same character in the story: passive, waiting, inert. In some strands of Buddhist philosophy, the emptiness at the root of things is not simple nothingness, but the absence of any independent, self-standing nature in the things we perceive, which is a different route through the same forest. But the forest is the same. The mystery of why anything is here at all, and the particular pressure that question exerts at night when the house is quiet. What altered the terms of the argument was not a philosopher's counter-argument. Nobody out-reasoned Leibniz. What altered the terms was a slow accumulation of measurements and equations, beginning in the early 20th century and still going on, which revealed that the universe has a history, a shape, and a budget, and most importantly, that what we mean by the word nothing is not what the universe means by it. Consider what Leibniz did not know, because the list is long, and every item on it bears directly on his argument. He did not know that the galaxies are flying apart from one another. He did not know that the cosmos began in a hot, dense state 13.8 billion years ago, and that time itself may have begun at the same moment, which means there may be no before in which a cause could have operated. He did not know that the total energy of the universe might be exactly zero. He did not know that the vacuum of space is not an absence but a physical substance with measurable properties that you can push against in a laboratory. Every one of those facts was waiting, buried in mathematics that had not been written and in starlight that had not yet been photographed. Leibniz was working with the only universe available to him, which was assumed to be eternal, static, and roughly the size of what a good telescope could see. He reasoned impeccably from a picture that turned out to be wrong in almost every particular. Let me place the central fact now, because everything tonight is built on it. In quantum field theory, which is, by any reasonable measure, the most precisely tested framework in the history of science, agreeing with experiment to 12 decimal places, in some cases the vacuum is never empty. At the smallest scales, space seethes with pairs of particles and antiparticles that appear, exist for an unimaginably brief interval, and vanish again. They are called virtual particles. They are not a metaphor, and they are not a bookkeeping trick. Their effects have been measured in laboratories, repeatedly, in more than one independent way. The vacuum has energy, it has structure, it has a kind of restless mechanical life, which means that the word nothing, as physics uses it, does not describe a state of pure absence. It describes a physical system sitting in its lowest possible energy state, and that state is not still, and it is not stable. That is the engine at the bottom of tonight's story. The universe does not require a creator to light the match, because on this account there was never an unlit match. The initial condition is not a tranquil void awaiting a divine breath. It is a condition that cannot persist. The transition from nothing to something is not a miracle. It is a phase change, or a tunneling event, or a fluctuation, depending on which physicist you ask, but in every version, it follows from the structure of reality rather than from an intervention in it. which raises the objection that the rest of the night has to answer, and it is a serious one. If the universe can emerge from nothing, how does it do that without violating the conservation of energy? The first law of thermodynamics is not a suggestion. Energy cannot be created or destroyed, only moved and transformed. And a universe is an enormous quantity of energy. Every star, every planet, every photon crossing the dark between them. To conjure all of that out of a void looks like the largest accounting fraud in history. There is a second problem sitting behind the first. If time itself began at the Big Bang, what could the word before possibly mean? A cause has to precede its effect. If there is no earlier moment, there is no room for a cause to stand in. Those are not rhetorical flourishes. They are the exact places where physics has done its deepest and most careful work, and each of them has an answer, or at least the beginning of one. To reach those answers, we have to start with a single word and take it apart. The word is nothing. In the laboratory, it collapses. For most of recorded history, a vacuum meant the complete absence of matter, a container with everything taken out, a space with no air, no dust, no atoms. Aristotle argued that nature abhors a vacuum, and for roughly 2,000 years that seemed self-evident because every time anyone tried to make one, something rushed in to fill it. The idea was not merely physical but almost moral. Emptiness was understood as a kind of wound in the world, which the world would immediately close. The first crack appeared in 1643, when Evangelista Torricelli filled a glass tube with mercury, sealed one end, and inverted it into a dish. The mercury fell, but it did not fall all the way. It settled at a column of about 76 centimeters and stopped, leaving a gap at the closed top of the tube. Something was in that gap, or nothing was. Torricelli argued for nothing that he had made a void, and that the mercury was held up not by any horror of emptiness, but by the weight of the air pressing down on the dish. Blaise Pascal took the argument up a mountain, the Puy de Dôme, in central France, and had his brother-in-law carry a mercury tube to the summit. The column dropped as the party climbed. There was less air above them, so the air pushed less hard. The vacuum was real, and the atmosphere had weight, and the world was not scandalized by emptiness after all. But even that vacuum was only an absence of matter. It was still a place, with dimensions, in which things could happen. And by the late 19th century, physicists had begun to suspect that the place itself had properties. James Clerk Maxwell's equations for electricity and magnetism, published in the 1860s, required empty space to have two specific numerical characteristics, a permittivity and a permeability, describing how readily electric and magnetic fields could establish themselves within it. Those two numbers, combined, gave the speed of light, which meant that the speed of light was not a property of light. It was a property of the vacuum. Light moved at 300,000 kilometers per second, because that is what empty space permits. The nothing was beginning to look like a something with specifications. The real fracture came with quantum mechanics. In 1927, Werner Heisenberg published the uncertainty principle, which states that certain pairs of physical properties cannot both be pinned down with arbitrary precision at the same time. The famous pair is position and momentum. The more exactly you know where a particle is, the less exactly you can know how fast it is going. And this is not a failure of instrumentation. It is a statement about what it means to be a particle. But there is a second pair, less famous and far more consequential for tonight: energy and time. Over a very short interval, the energy of a system is not sharply defined. It cannot be. And that has a startling consequence. For extremely brief durations, energy does not have to be strictly conserved. A system can borrow from the vacuum, provided it repays the loan quickly enough that no measurement lasting longer than the loan could ever detect the discrepancy. The size of the loan and the length of the loan are inversely related. Borrow a little, and you can keep it for a comparatively long time. Borrow a great deal, and you must return it almost instantly. At the scale where quantum gravity is expected to matter the Planck time, roughly 10 to the minus 43 seconds, a number so small that writing it out would take a line of zeros longer than this sentence. The permitted borrowing is enormous, but the implication runs in the other direction too. If the vacuum is subject to the uncertainty principle, then it cannot sit at exactly zero energy with perfect confidence. because that would be a state precisely specified for all time. It must fluctuate. At every point in space, at every moment, pairs of particles and antiparticles flash into existence, exist for an instant, and annihilate one another, returning what they borrowed. Space is not a stage. Space is weather. The first person to look directly at this and describe what he saw was Paul Dirac, a British physicist so silent in conversation that his colleagues at Cambridge jokingly defined a unit of speech, 1 Dirac, equal to 1 word per hour. In 1928, Dirac was trying to reconcile quantum mechanics with special relativity, two theories that worked beautifully and separately and refused to work together. He produced an equation describing the electron that fitted the experimental data with startling accuracy. It also predicted something absurd. For every solution describing an electron with positive energy, the equation produced a mirror solution describing a particle with negative energy. Negative energy states should not exist. Worse, if they did, every electron in the universe would immediately cascade down into them, radiating light as it fell, and all ordinary matter would disintegrate in a fraction of a second. Dirac did not discard the solutions. In 1930, he proposed instead that all of the negative energy states were already occupied, that what we call empty space is in fact an infinite sea of electrons, filling every available negative energy level, and that ordinary matter floats on top of it. Electrons cannot fall into the sea because there is no room, and if you could knock one electron out of the sea, the hole it left behind would move and behave exactly like a particle with the same mass as an electron and the opposite charge. 2 years later, at Caltech, Carl Anderson was photographing cosmic ray tracks in a cloud chamber and found one that curved the wrong way in a magnetic field. He had photographed the hole. The positron, the electron's antimatter twin, was real, and Dirac had predicted it out of an equation he had not fully believed. Dirac's infinite sea is not how modern physics describes the vacuum. Quantum field theory replaced it with something both simpler and stranger, in which particles are excitations in fields that fill all of space, and the vacuum is those fields sitting in their lowest state. But the sea did something important. It made the vacuum into a place with contents. It cracked the door. The door swung wide in June of 1947, on Shelter Island, off the eastern tip of Long Island, where about 24 of the best physicists in America gathered for 3 days at a small inn to discuss what was wrong with their theories. Willis Lamb, of Columbia University, presented a measurement. Using microwave techniques developed during the war for radar, Lamb and his student Robert Rutherford had examined the energy levels of hydrogen, the simplest atom there is. 1 proton and 1 electron, the thing every theory has to get right before it is allowed to attempt anything else. Dirac's equation predicted that 2 particular energy levels in hydrogen should be exactly identical. Lamb found that they were not. The gap was minuscule, about 1 part in 10 million of the energy involved, but it was there, and his measurement was clean enough that it could not be argued away. Hans Bethe worked out what it meant on the train home from the conference. Sitting in a carriage from New York to Schenectady, with no reference books and no computer, he did an approximate calculation on paper and found that the shift came from the electron interacting with the vacuum. The electron is not orbiting a proton in empty space. It is orbiting in a medium that is constantly flickering, and those flickers jostle it, very slightly, altering its energy. The effect had been sitting inside the theory all along, and nobody had thought to look for it, because nobody had believed the vacuum was the sort of thing an electron could bump into. The Lamb shift was the first direct experimental evidence that empty space is not empty. It is also, as a matter of history, the measurement that forced the development of modern quantum electrodynamics, the theory that would eventually agree with experiment better than any other theory humans have ever constructed. Then, in 1948, the Dutch physicist Hendrik Casimir turned the vacuum into something you could push. Casimir was working at the Philips Research Laboratories in Eindhoven on a resolutely practical problem: why suspensions of tiny particles in liquid sometimes clump together and ruin the product. He and his colleague Dirk Polder were calculating the weak attractive forces between neutral molecules. Niels Bohr, hearing about the work, suggested to Casimir that he think about it in terms of the zero-point energy of the electromagnetic field. Casimir did, and the result was one of the strangest predictions in 20th century physics. Take 2 perfectly flat, uncharged metal plates, place them in a vacuum, parallel, and bring them very close together, closer than a millionth of a meter. The vacuum fluctuations between the plates are now constrained. Only those with wavelengths that fit neatly into the gap can exist there. Outside the plates, there is no such restriction, and fluctuations of every wavelength continue as normal. The result is an imbalance in pressure. There is more vacuum pushing inward from outside than pushing outward from between. The plates are shoved together by nothing at all. The prediction was published, admired, and then left alone for the better part of 50 years because the force is extraordinarily weak and the plates have to be aligned with a precision that was simply not available. At a separation of 10 nanometers, the pressure is roughly 1 atmosphere, which sounds substantial until you realize how difficult it is to hold two plates parallel across that distance without them touching. Early attempts produced results consistent with the prediction, but with error bars wide enough to drive through. In 1997, Steve Lamoureux, then at the University of Washington, sidestepped the alignment problem elegantly by using a metal sphere approaching a flat plate rather than two plates, hanging the apparatus from a torsion pendulum, and measured the Casimir force to within about 5% of the predicted value. Others refined it further. The vacuum pushes. It has a mechanical presence you can measure with a pendulum. There is a third piece of evidence, and it is the one that connects the vacuum most directly to gravity. In 1974, Stephen Hawking showed that the fluctuations of the vacuum near the event horizon of a black hole do not always annihilate cleanly. Occasionally, one member of a virtual pair falls inside the horizon while the other escapes, and the escaping particle becomes real, carrying away energy that the black hole must pay for out of its own mass. Black holes evaporate. They do it absurdly slowly. A black hole the mass of the Sun would take longer than 10 to the 67 years to disappear, which is an interval next to which the current age of the universe is not worth mentioning, but they do it. That result has never been directly observed, and it may never be, but it is derived from taking vacuum fluctuations seriously in curved spacetime, and it is regarded by most physicists as very likely correct. So what has become of the word nothing? In the laboratory, a vacuum is not an absence. It is a physical system with a definite energy density, with a permittivity and a permeability, with a zero-point energy that cannot be removed by any procedure because the uncertainty principle forbids removing it. You cannot cool it away, you cannot pump it out. If you could somehow suppress every field to exact stillness, the suppression itself would be a violation of quantum mechanics. The vacuum is the lowest rung on the ladder, and the lowest rung is still a rung, which leaves us with a genuine problem, and it is worth naming clearly rather than sliding past it. Virtual particles are evanescent. They flicker and die. The universe is not evanescent. It is an enormous population of real, persistent particles that has been here for 13.8 billion years and shows no sign of being repaid. Everything we have established in this section shows that the vacuum is alive. None of it shows how a cosmos-sized quantity of lasting energy could come out of it and stay. The energy of a virtual particle is borrowed against the uncertainty principle and must be returned almost immediately. The universe is a loan that was never called in. That is a different problem, and it has a different answer, and the answer requires knowing something Leibniz could not have known, and Casimir did not need to. It requires knowing that the universe has not always looked like this. Before anyone could ask where the energy came from, somebody had to notice that the sky is not still. For most of human history, the universe was assumed to be static, eternal, and unchanging. A fixed arena in which stars wheeled and planets turned, and nothing fundamental ever happened. This was not a naive belief. It was the only arrangement that made sense, because the alternative carried a cost nobody wanted to pay. If the universe had a beginning, then something started it, and that something would demand an explanation of a kind physics could not supply. Better to assume eternity and let the heavens look after themselves. Albert Einstein ran into this directly. In 1917, 2 years after completing general relativity, he applied his field equations to the universe as a whole and found that they refused to sit still. The equations described a cosmos that must either expand or contract. There was no stable middle. Space filled with matter would collapse under its own gravity unless something held it apart. So Einstein added a term, a small repulsive pressure built into space itself, which he called the cosmological constant, and tuned it precisely to cancel the collapse. It was a patch, and he knew it was a patch. He was adjusting the mathematics to match an assumption about the world that he had inherited rather than tested. The light was already telling a different story. It had been telling it for 5 years, in Arizona, to a man almost nobody has heard of. At the Lowell Observatory in Flagstaff, Vesto Slipher had been assigned what his employer considered a side project. Percival Lowell, who had founded the observatory largely to look for canals on Mars, wanted the spiral nebulae examined, those faint whirlpool smudges scattered across the sky, which were then thought to be solar systems in the process of forming. Slipher attached a spectrograph to the 24-inch refractor and began the extraordinarily slow work of gathering enough light from an object that faint to spread it into a spectrum. Individual exposures ran for 20, 30, 40 hours, accumulated across multiple nights in an unheated dome in the mountains of northern Arizona in winter. In 1912, he obtained a good spectrum of the Andromeda Nebula and found its lines shifted toward the blue. It was moving toward us at about 300 kilometers per second, faster than anything anyone had measured. He kept going. By 1914, he had a dozen more, and the pattern had inverted. Almost all of the others were shifted the other way, toward the red. Their light stretched to longer wavelengths as though the objects were racing away. By 1917, he had measured 25, and 21 of them were receding, some at more than 1,000 kilometers per second. Slipher, a cautious and methodical man who published little and claimed less, did not say what it meant. He said what he had measured. It would be more than a decade before anyone assembled his numbers into a picture. Part of the delay was that nobody knew how far away the nebulae were, and without distances the velocities were just a curiosity. Solving that required a different kind of work, done by a woman who was not permitted to operate a telescope. Henrietta Swan Leavitt worked at the Harvard College Observatory as one of a group of women hired to examine photographic plates and catalogue what was on them. They were called computers, and they were paid around 30 cents an hour, and they were not allowed to direct their own research. Leavitt was assigned variable stars in the Magellanic Clouds. She found more than 2,000 of them, and in a class of variable star called Cepheids, stars that brighten and dim in a regular cycle, over days or weeks she noticed something that had no obvious reason to be true. The brighter the star, the longer its cycle. Because all the stars she was studying sat inside the same cloud, they were all at roughly the same distance, which meant the differences in apparent brightness were real differences in output rather than artifacts of distance. In 1912, she published the relationship. Measure how long a Cepheid takes to pulse, and you know its true luminosity. Compare that to how bright it appears, and you know how far away it is. She had built the first reliable measuring rod for the universe beyond our own neighbourhood. She was given almost no credit for it during her lifetime. She died of cancer in 1921, at 53. A Swedish mathematician wrote to Harvard 4 years later hoping to nominate her for the Nobel Prize, and was informed that she was dead and therefore ineligible. Her measuring rod arrived in time for one of the great public disputes in the history of astronomy. In April of 1920, at the Smithsonian in Washington, Harlow Shapley and Heber Curtis argued in front of an audience about the scale of the universe. Shapley held that the Milky Way was the entire cosmos, and that the spiral nebulae were nearby clouds of gas within it. Curtis held that the nebulae were separate galaxies, comparable to our own, at enormous distances. Both men had good arguments and both were partly wrong, and the debate settled nothing on the night. It was settled 3 years later, alone, in the dark, by a man on a mountain in California. In October of 1923, Edwin Hubble was photographing the Andromeda Nebula with the 100-inch telescope at Mount Wilson, then the largest in the world. He was looking for novae. On a plate taken on the 6th of October, he found what he thought was 1 and marked it with an N. Comparing it against earlier plates, he realized the star was not a nova at all. It was brightening and dimming on a cycle. It was a Cepheid. He crossed out the N and wrote, in red, a single word, var, short for variable, followed by an exclamation mark. That plate still exists, with a correction on it. Applying Leavitt's relationship gave a distance of roughly 900,000 light-years, far beyond any plausible boundary of the Milky Way. The number was too small, as it turned out, by a factor of about 2.5, but it was large enough. Andromeda was not a cloud in our galaxy. It was another galaxy, and the universe was immeasurably bigger than the argument in Washington had assumed. Meanwhile, the theory had been quietly waiting. In 1922, the Russian mathematician Alexander Friedmann had taken Einstein's field equations without the cosmological constant and worked out the family of solutions they permit for a universe that is roughly uniform on large scales. He found that they describe universes that expand or contract or expand and then fall back. None of them sit still. Einstein's first response was to publish a note asserting that Friedmann had made an arithmetic error. He had not, and Einstein retracted the criticism the following year, though without much enthusiasm. Friedmann never saw his solutions confirmed. He died in 1925, aged 37, of typhoid fever contracted on holiday. The man who assembled the pieces was Georges Leavitt, a Belgian priest who had served as an artillery officer in the First World War, then studied at Cambridge under Arthur Eddington, and afterwards in the United States, where he met Slipher and Hubble and read their data. In 1927, he published a paper deriving, independently of Friedmann, an expanding solution to Einstein's equations, and going further, predicting that galaxies should be observed to recede at speeds proportional to their distance, and using the available measurements to estimate how fast. He published it in an obscure Belgian journal, in French. Almost nobody read it. When Lemaitre described the work to Einstein at a conference in Brussels that year, Einstein told him that his calculations were correct, but his physics was abominable. 2 years later, in 1929, Hubble published the relationship with a larger and better dataset, combining his own Cepheid distances with redshifts measured mostly by Slipher, and the result was unmistakable even though the scatter was considerable. The farther a galaxy is, the faster it is going away. The universe is expanding. The number Hubble derived for the rate of that expansion was badly wrong, about 500 kilometers per second per megaparsec, roughly 7 times the modern value, because his distance calibration was off. There are 2 distinct populations of Cepheid variable, with different luminosities, and nobody would work that out until the 1950s. His galaxies were farther away than he thought, and the expansion slower. Taken at face value, his number implied a universe younger than the rocks in the ground, which was one of the strongest arguments against the whole picture for 2 decades. But the shape of the relationship held, and the shape was what mattered. The cosmos was not an arena, it was breathing outward. Lemaitre did not fight over priority. He was a reserved man, more interested in the implication than the credit, and when his 1927 paper was translated into English in 1931, the paragraphs estimating the expansion rate were left out a deletion, long attributed to suppression, and now generally believed to have been made by Lemaitre himself, on the grounds that Hubble had since done it better. That same year he published the implication he had been circling. If the universe is expanding, then running the film backwards brings everything closer together, and closer, until the entire cosmos is compressed into a single point of unimaginable density. He called it the primeval atom, and he called the moment it broke apart the day without yesterday. It was the first clear statement of what would become the Big Bang, and it was made by a man in a clerical collar who was careful for the rest of his life to insist that it was a physical hypothesis and not a theological one, and who objected publicly when a pope tried to claim it as proof of Genesis. Einstein came round. He met Lemaitre several times and eventually dropped the cosmological constant entirely. The famous story is that he called it his greatest blunder, though the phrase reaches us second-hand through George Gamow, and Lemaitre himself said he never heard Einstein use those words. What is certain is that he accepted the expansion, and that he remained uncomfortable with what it implied about a beginning. He was not alone in that discomfort. Fred Hoyle, a Yorkshireman of formidable ability and equally formidable stubbornness, never accepted a sudden origin at all. In 1949, speaking on the radio in Britain, he referred dismissively to the hypothesis that all the matter in the universe was created in one big bang. He meant it as ridicule. The phrase escaped him and became the name of the theory he had spent the sentence attacking. Hoyle spent decades promoting the alternative he had developed with Hermann Bondi and Thomas Gold, the steady-state model, in which the universe expands forever, but new matter is continuously created in the gaps, at a rate of roughly 1 hydrogen atom per cubic meter every billion years, so that the large-scale picture never changes and there is no beginning to explain. It was elegant, and it was wrong. But Hoyle's resistance was not simple obstinacy, and the irony of his career is worth sitting with. It was Hoyle, more than anyone, who worked out how the heavy elements are made. In 1957, with Margaret and Geoffrey Burbidge and William Fowler, he published the paper explaining how stars fuse hydrogen into helium and helium into carbon and onward up the periodic table, and how they scatter the results when they die. The man who refused to believe the universe had a beginning explained where everything in your body came from. He also predicted, in advance, a specific energy level in the carbon nucleus that had to exist for the process to work, and it was found where he said it would be. It is worth noting how close the steady-state model came to being reasonable, because it is usually described as though it were obviously silly. Creating 1 hydrogen atom per cubic meter every billion years is a rate so low that no experiment then or now could rule it out directly. And the model had a genuine advantage over its rival, for Hubble's badly calibrated expansion rate implied a universe younger than the Earth, which is a serious problem for a theory of the beginning, and no problem at all for a theory with no beginning. Steady state was not defeated by argument. It was defeated by a measurement nobody was looking for. The point on which Hoyle would not yield was the sharpest one available, and it takes us back to Leibniz. Rewind the expansion far enough, and you reach a state in which all of space, all of matter, and all of energy are compressed into something infinitely dense and infinitely hot, a singularity. At that point, the equations of general relativity stop producing answers. They do not produce wrong answers. They produce infinities, which is the way a theory has of announcing that it has been taken outside its own domain. Time, as far as the mathematics can tell us, does not extend past it. Asking what came before is like asking what lies north of the North Pole. The question is grammatical, and it has no referent. That is not an explanation. It is a boundary. And the boundary is exactly where the old argument reasserts itself. If the universe began at a specific moment, and if there is no time before that moment, then a creator could not have acted within time to bring it about. But could something have acted from outside time altogether? Physics has nothing to say about that, and honesty requires admitting it. What physics can do is ask a narrower and much more answerable question. Never mind who or what. Where did the energy come from? The Big Bang gave the universe a birth certificate, but no explanation of the inheritance. It does not tell us how the infant cosmos came to contain the staggering quantity of energy we can still account for today, every star, every planet, every photon in the ancient background radiation still washing through space. And the first law of thermodynamics is perhaps the most deeply ingrained principle in all of physics. Energy is neither created nor destroyed. It only changes form. A universe appearing out of nothing looks like a violation of that law on the largest imaginable scale. If conservation of energy is absolute, then the universe should not be here. It is here. So one of those two statements needs work. The objection is powerful because it is intuitive. You cannot get something for nothing. Every child learns this, and nothing in ordinary life ever contradicts it. But the books do balance, and the reason they balance was hidden inside the most famous equation ever written, and inside a much older piece of mathematics that had been sitting in plain view since Newton. In 1905, Einstein published a paper on the electrodynamics of moving bodies, which we now call special relativity, and then, later the same year, a 3-page supplement asking whether the inertia of a body depends on its energy content. The answer was yes, and completely. Mass is energy, held in a very concentrated form. The exchange rate is the speed of light squared, which is an enormous number, which is why the conversion is so violent when it happens. A single gram of matter, converted entirely, would release around 90 trillion joules. That is roughly the yield of the bomb dropped on Nagasaki, from a mass smaller than a paperclip. So when we ask where the universe came from, we are asking where an unimaginable quantity of energy came from, because that is what matter is. Every atom in your body, every grain of sand on every shore, every star burning in every galaxy, all of it is energy, wearing a solid disguise. The intuitive answer is that it must have been put in from outside, injected into a void by something with the resources to do it. That is Leibniz's intuition, dressed in 20th century clothes. But there is a second column in the ledger, and almost nobody thinks about it, because it is taught early and then never used again. Gravitational potential energy is negative. This is standard first-year physics. If you hold a rock above the floor, it has potential energy relative to the floor, which you can release by letting go. But potential energy is always defined relative to a reference point, and the natural reference point in gravity is infinity, the energy a body would have if it were infinitely far from everything else, feeling nothing. Bring two masses together from infinity, and they release energy as they fall toward each other, which means that any bound configuration has less energy than the same matter spread out. And if you set the scattered state at 0, the bound state is below 0, negative. Watch what happens in a collapsing cloud of gas. It contracts under its own gravity, and as it contracts it heats up, and the heat radiates away as light. Energy leaves the system in enormous quantities, for millions of years, and at the end you have a star hotter, denser, and containing less total energy than the diffuse cloud it came from. The light pouring out of a young star is not created by the collapse. It is paid for by the gravitational field going further into debt. Scale that up. Every galaxy is a deep well of negative gravitational energy. Every cluster of galaxies is a deeper one. The matter inside them carries positive mass energy. And the extraordinary thing, noticed in pieces across the 20th century, is that for a universe like ours, those two columns are not merely comparable in size, they can cancel. Exactly. The first person to say so out loud was Pascual Jordan, one of the founders of quantum mechanics, whose name is missing from most popular accounts, partly because of his later membership of the Nazi Party. In the 1920s, walking with George Gamow, Jordan speculated that a star might be created from nothing, because its positive mass energy could be precisely offset by the negative energy of its own gravitational field. The net cost would be 0. Gamow, by his own account, mentioned the idea to Einstein while they were crossing a street in Princeton, and Einstein stopped walking in the middle of the road, and they were nearly run over. Jordan's version was crude and never developed, but it contained the seed of the question. If a star can, in principle, cost nothing, what about a universe? Richard Feynman gave the idea its most useful picture. Lecturing on gravitation at Caltech in the early 1960s, he asked his students to imagine a man digging a hole in flat ground. The dirt piles up beside the hole. The pile is positive it is something that was not there before, and you can measure it. The hole is negative. It is an absence of exactly the same amount. Count the total change in the amount of dirt at that spot and the answer is 0. Nothing was created. Something was rearranged into a pile and a hole. Feynman suggested the universe works the same way. Matter is the pile. The gravitational field binding it is the hole. Add them and you may get nothing at all. The person who asked the question with a straight face and put it in print was Edward Tryon, and the story of how he came to do it is one of the better anecdotes in modern physics. In the late 1960s, Tryon was a graduate student at Berkeley, attending a seminar by Sidney Coleman. During a pause, Tryon spoke up and suggested that perhaps the universe is a vacuum fluctuation. The room laughed. Tryon assumed for years afterwards that he had said something foolish and mostly kept quiet about it. In 1973, by then at Hunter College in New York, he wrote it up properly and sent it to Nature, under the title, "Is the Universe a Vacuum Fluctuation?" The argument was compact. If the total energy of the universe is 0, then quantum mechanics places no lower bound on how long such a fluctuation can persist, because the uncertainty relation between energy and time only constrains loans that have to be repaid. A loan of 0 can be held forever. Tryon's paper ended with a line that is unusual in a physics journal, and has been quoted ever since, that the universe is simply one of those things which happen from time to time. It was largely ignored for a decade. It is now recognized as the first serious statement of the idea. Stephen Hawking gave it the phrasing that reached the public. In A Brief History of Time, in 1988, he wrote that the negative gravitational energy exactly cancels the positive energy represented by the matter, and so the total energy of the universe is 0. He called it the ultimate free lunch, a phrase he borrowed from the physicist Alan Guth, who will matter a great deal shortly. It is important to be honest about how firm this is, because it is repeated far more confidently in popular accounts than it deserves. Defining a global energy for the whole universe is genuinely difficult in general relativity, and not because of a technical gap we expect to close. In a curved, expanding spacetime, there is in general no unique way to add up all the energy in a region and get a single number that stays constant, because the symmetry that guarantees energy conservation in ordinary physics, the fact that the laws are the same yesterday and today, does not hold globally in a universe whose geometry is changing. Energy conservation, as most people learn it, is a local statement in general relativity, not a cosmic one. There is a name attached to why energy is conserved at all, and it belongs to someone who was not permitted to hold a paid academic position for most of her career. In 1915, at Göttingen, Emmy Noether was asked by David Hilbert and Felix Klein to help with a problem that had appeared in Einstein's new theory. Energy conservation, which worked flawlessly everywhere else in physics, was behaving strangely in general relativity, and nobody could say why. Noether solved it, and the solution was far larger than the problem. She proved that every conservation law in physics arises from a symmetry. Conservation of momentum comes from the fact that the laws are the same here as over there. Conservation of angular momentum comes from the fact that they are the same whichever way you face. And conservation of energy comes from the fact that they are the same today as they were yesterday. The symmetry of physics under translation in time. That is the whole reason energy is conserved, not a substance that cannot be destroyed, a consequence of the laws not changing with time, which tells you immediately where the loophole is. In a universe whose geometry is itself changing, the symmetry that guarantees global energy conservation is not available, and the conservation law does not apply in the form everyone learns at school. This is not a dodge invented to rescue cosmology. It is a theorem, proved in 1918, sitting at the foundation of the subject. Noether was refused a salaried post at Göttingen for years on the grounds of her sex, and lectured under Hilbert's name to get around it. Hilbert, arguing her case to the faculty senate, is supposed to have said that he did not see how her sex was an argument. Since this was a university and not a bathhouse, she was dismissed by the Nazi government in 1933 and died in the United States 2 years later, at 53. Einstein wrote her obituary for the New York Times. There is one clean case. For a universe that is spatially closed, one that curves back on itself, finite in extent with no boundary, the total energy can be calculated rigorously and it is exactly zero. Not approximately. Exactly. The positive contribution of everything inside is precisely matched by the negative curvature energy of the geometry that contains it. Our universe appears to be flat, or so close to flat that we cannot distinguish it, which sits on the boundary between closed and open. In that case, the argument is more delicate, and the community is not unanimous. Some physicists regard the zero-energy universe as a solid result. Others regard it as a suggestive heuristic that has been leaned on too hard. Both positions are held by serious people, and it is worth knowing that rather than being handed a conclusion, but the load-bearing point survives the caution, and it is narrower than the popular version, and stronger for being narrow. There is no law of physics prohibiting a universe from coming into existence with zero net energy. The conservation of energy is not violated by such an event, because nothing was ever created. The question, where did all the energy come from, turns out to contain a false assumption, in the same way that asking who is winning a game of solitaire does. The positive and negative columns sum to nothing. They always did. There was no fortune to be bestowed, and therefore no benefactor required. The universe looks like an impossible gift. It is not a gift. It is a transaction that nets to zero, entered into by nobody, on behalf of nobody. The pile and the whole, the stars and the gravity that holds them. Add the columns and the sum is silence, which opens the door but does not walk through it. A quantum event, permitted by the uncertainty principle, could, in principle, produce a universe without borrowing any net energy from anywhere. Fine, but the vacuum produces such events constantly, everywhere, and they vanish immediately. A permission is not a mechanism. A quantum fluctuation at the Planck scale is unimaginably small. A speck of space-time, far smaller than a proton, lasting less than a trillionth of a second. How does a speck like that become 100 billion galaxies spread across a sky that looks the same in every direction? The answer was hiding inside a problem the Big Bang could not solve on its own. By the late 1970s, the Big Bang model was in good shape. The expansion had been confirmed, the ancient background radiation had been found, and the measured abundances of the lightest elements matched what the theory predicted for the first 3 minutes with an accuracy nobody had expected. But 3 problems sat inside it, and they were not minor irritations. They were structural, and each of them pointed at the same uncomfortable place, the initial conditions, which the theory did not explain and simply had to assume. The first is the horizon problem. Look in one direction and measure the temperature of the background radiation. Look in exactly the opposite direction and measure it again. The 2 numbers agree to within about 1 part in 100,000. That should be impossible. Those 2 patches of sky have never been in contact. Light has not had time, in the entire history of the universe, to travel from one to the other. No signal has passed between them, no heat has flowed, nothing has ever equalized. And yet they are the same temperature to 5 decimal places, 2 thermometers in rooms that have never shared air, reading identically. The second is the flatness problem. The geometry of the universe is Euclidean to within our ability to measure it. Parallel lines stay parallel. Triangles have angles that sum to 180 degrees. But in the standard Big Bang, flatness is an unstable equilibrium. Any tiny departure from it grows over time and grows fast. A pencil balanced perfectly on its point will stand there indefinitely in principle and will fall over immediately in practice, because perfection is a set of measure 0. For the universe to be as flat as we measure it now, after 13.8 billion years of amplification, the density in the first instance must have been tuned to the critical value to something like 1 part in 10 to the 60th. That is not a coincidence anyone can be comfortable with. The third problem was more technical and, at the time, more fashionable. The grand unified theories then being developed predicted that the phase transitions of the very early universe should have produced magnetic monopoles, isolated north or south magnetic poles, extremely massive, extremely stable in enormous numbers, enough of them that they would dominate the mass of the universe today. None has ever been detected, not one. The universe was too smooth, too flat, and too clean. In December of 1979, a young particle physicist named Alan Guth was working at Cornell on a postdoctoral position in what he later described as an academic career that appeared to be going nowhere. He was 32 and had already had 3 temporary appointments. He was not trying to solve the horizon problem. He was not thinking about flatness. He was working on monopoles because a colleague had suggested it, and monopoles were a particle physics problem rather than a cosmological one. What he was studying was the behavior of scalar fields in the early universe fields that can take a uniform value across all of space and store energy in that value, rather like a tension, and he realized that such a field could get stuck. If the field found itself in what is called a false vacuum, a state that is stable against small disturbances but is not the true lowest energy state, a ball resting in a shallow dip partway down a hillside, rather than in the valley floor, then it would sit there, holding its energy, unable to release it. And a false vacuum has a bizarre gravitational property. Its energy density stays constant as space expands, which means its pressure is negative, which means, in general relativity, that it pushes rather than pulls. Gravity reverses sign. Instead of drawing space together, it drives it apart, and it drives it apart exponentially doubling, then doubling again, each doubling taking the same brief interval as the last. Guth worked out that night what such an episode would do, and wrote in his notebook, in capital letters and underlined twice, the words, "spectacular realization." He had solved all 3 problems at once, with a mechanism he had not been looking for. The horizon problem dissolves because the entire observable universe was, before the expansion, a single patch small enough to have equalized its temperature in the ordinary way. Everything we can see was once in contact. Then it was stretched apart faster than light could follow, carrying its uniformity with it, so that regions that appear to have no shared history, in fact, have nothing but shared history. The flatness problem dissolves because the stretching irons out curvature, take any surface, however crumpled, and expand it by a large enough factor, and any local patch of it becomes indistinguishable from flat. The Earth is a sphere and your garden is level. Inflation does this to the geometry of the cosmos, by a factor so large that whatever curvature the universe started with is undetectable now. And this makes flatness a prediction rather than a coincidence, which is a much stronger position for a theory to be in. The monopole problem dissolves because whatever population of monopoles existed before the expansion was diluted by the same enormous factor. If you start with a monopole in every cubic centimetre and then increase every distance by a factor of 10 to the 26, you end up with perhaps one monopole in the entire visible universe, which is consistent with never finding one. The numbers involved are worth stating plainly because they are hard to hold. The episode lasted somewhere around 10 to the minus 36 seconds, a fraction of the first instant, so small that calling it a fraction of a second is misleading. In that interval, a region far smaller than a single proton was stretched by a factor of at least 10 to the 26, and probably far more. That is the difference between the width of an atomic nucleus and the distance to a nearby galaxy, accomplished in less time than light takes to cross an atom. And nothing violated relativity in the process, because nothing was travelling through space. Space itself was expanding, and there is no speed limit on that. 2 points can be carried apart faster than light can bridge the gap between them, and are constantly at the edge of what we can see right now. When the field finally rolled off its ledge and fell into the true vacuum, it dumped all of its stored energy at once into a hot, dense soup of particles and radiation. That event is called reheating, and in this picture, it is what we have always meant by the Big Bang. The Big Bang was not the beginning of the universe. It was the moment inflation ended, the engine shutting off and handing over to the fireball whose glow we can still photograph. Guth's original version had a fatal flaw, and to his credit he identified it himself and put it in his own paper. The false vacuum decays the way boiling water does, in bubbles. Bubbles of true vacuum nucleate at random points and expand into the surrounding false vacuum. The trouble is that the space between the bubbles is still inflating, faster than the bubbles can grow into it, so the bubbles never merge. You end up with a violently inhomogeneous mess, a foam of disconnected regions, nothing like the smooth universe we live in. Guth called this the graceful exit problem, and could not solve it. It was solved twice, independently. In 1981 and 1982, André Linde, working in Moscow, proposed what became known as new inflation, and Andreas Albrecht and Paul Steinhardt at the University of Pennsylvania arrived at essentially the same idea. Instead of a field trapped behind a barrier and tunneling out in bubbles, imagine a field on a very gently sloping plateau, rolling slowly downhill. While it rolls, its energy is nearly constant and inflation proceeds. When it reaches the steep part, it accelerates, falls into the valley, oscillates, and reheats everywhere at once, smoothly, without bubbles. This is called slow roll inflation, and it is the version that survives. Now comes the part that turned inflation from a clever fix into a testable science, and it is, to my mind, the single most remarkable claim in modern cosmology. Quantum mechanics does not take a holiday during inflation. The field driving the expansion is a quantum field, and it obeys the uncertainty principle like everything else, which means its value at any point flickers. At any instant, some regions have slightly more of it than others. These are the same vacuum fluctuations we met in the laboratory, the ones that shift the energy levels of hydrogen and push metal plates together. Ordinarily, they vanish as fast as they appear. But during inflation, space is expanding so violently that a fluctuation can be stretched beyond the distance over which it could smooth itself back out. It is torn apart faster than it can heal, and so it freezes, locked in, no longer a quantum flicker but a permanent, classical variation in the density of the region. Inflation ends. The frozen pattern is inherited by the hot matter and radiation that follows. More. Regions with slightly more energy have slightly more gravity, and pull in more material, and get denser, and pull in more still. Over hundreds of millions of years, the slightly denser patches become gas clouds, then the first stars, then galaxies, then clusters of galaxies. The slightly emptier patches become voids, which means that every structure you have ever seen or heard of, every galaxy, every star, every planet, the arrangement of the constellations, the cosmic web of filaments that maps the largest scales we can survey, began as a quantum fluctuation in a field, in the first fraction of the first second, stretched to astronomical size, and then frozen in place. The distribution of matter across billions of light years is a photograph of quantum noise, blown up beyond any conceivable magnification and left on the wall. That is a very specific claim, and specific claims can be checked. Inflation predicts not just that there should be primordial density variations, but roughly what they should look like statistically. It predicts a nearly scale invariant spectrum, approximately the same amount of variation on every size scale with a slight tilt, so that the fluctuations are marginally stronger on large scales than small ones. It predicts that the variations should be Gaussian, distributed in the familiar bell curve way, because they came from quantum noise rather than from any organized process. It predicts that the universe should be flat, to high precision, and it predicts that the fluctuations should be adiabatic, meaning that the ordinary matter, the dark matter, and the radiation all vary together, rather than independently, because all of them inherited the same pattern from the same field. None of those predictions was guaranteed by any other theory. Several of them were made before there was any instrument capable of testing them. There is a consequence of slow roll inflation that Lind noticed almost immediately, and that nobody has been able to get rid of since, and it will matter at the end of tonight. If the field is rolling slowly down a plateau, then quantum fluctuations are jostling it as it goes the same fluctuations that seed the galaxies. Most of the time, those jostles are small compared to the rolling and make little difference. But in some regions, by chance, the fluctuation kicks the field back up the slope rather than down it. Those regions keep inflating while their neighbours finish. And because inflating regions double in volume repeatedly while finishing regions do not, the still inflating volume outgrows the finished volume, no matter how rare the upward kicks are. The result is that inflation, once started, does not stop. It stops here and there, producing pockets that become hot, ordinary universes, while the space between them continues to inflate and produce new pockets forever. Lind called it eternal inflation, and the striking thing is that it was not put in by hand. It falls out of taking quantum mechanics seriously in a theory built for entirely different reasons. What was needed was a photograph of the universe taken before any of the structure had formed a picture of the frozen pattern itself, before gravity had begun to work on it. That picture exists. It is the oldest light in the universe, and it has been falling on the Earth continuously since long before the Earth was here. It had also been predicted, decades earlier, by people who had no idea it would ever be found, and then forgotten, and then rediscovered by two engineers who spent nearly a year trying to get rid of it. The prediction came out of an attempt to explain something else entirely, which is how most of the best predictions arrive. In the late 1940s, George Gamow was trying to work out where the chemical elements came from. Gamow was a Russian émigré with an enormous appetite for practical jokes and a habit of thinking about the early universe as a physical laboratory rather than a philosophical problem. His idea was that if the cosmos began hot and dense, it would have been a nuclear furnace, and everything in the periodic table might have been cooked in the first few minutes. His doctoral student, Ralph Alpher, did the calculations. The paper appeared in 1948, and Gamow, unable to resist, added the name of Hans Bethe to the author list, purely so that the byline would read Alpha, Bather, Gamow, a pun on the first three letters of the Greek alphabet. Bethe had contributed nothing to it, and cheerfully allowed his name to stay. It was published on the 1st of April. The physics was serious, and partly right. The first few minutes did cook the light elements, and the calculations of how much hydrogen, how much helium, how much lithium, refined over the following decades, are now one of the strongest pillars of the whole picture. But it could not make anything heavier than lithium, because the expanding universe cooled below the fusion threshold too quickly, and because there is no stable nucleus with 5 or 8 particles in it, which creates a gap the process cannot bridge. Everything above lithium is made in stars, which is what Hoyle worked out, while insisting the Big Bang had not happened. Alpha, working now with Robert Herman, then pushed the reasoning one step further, and this is the step that matters tonight. If the early universe was that hot, it was filled with free electrons, and free electrons scatter light ferociously. A photon could travel almost no distance before being deflected. The universe was opaque, not dark, but foggy, a glowing fog with no line of sight through it. As space expanded, it cooled, and at a temperature of around 3000 Kelvin, roughly 380,000 years after the beginning, something changed abruptly. The electrons slowed enough to be captured by nuclei and bound into neutral atoms. The fog cleared. In an interval that was, cosmologically speaking, almost instantaneous, the universe went from opaque to transparent, and every photon that happened to be traveling at that moment was suddenly free to keep going. Those photons are still going. They have been traveling for 13.8 billion years, stretched by the expansion of space the entire way, cooled from the fierce orange glow of a 3,000-degree fog down into the microwave band. Alpha and Hermann calculated where the temperature should be now and got about 5 degrees above absolute zero. Nobody paid attention. The prediction was published, correct, and comprehensively ignored, partly because no instrument existed that could have tested it, and partly because Gamow's group had a reputation for exuberance that did not encourage careful reading. Alpha and Hermann moved on to other work, both eventually leaving academic research for industry. Alpha would spend the rest of his life being quietly bitter about it, with justification. 15 years later, at Princeton, Robert Dicke arrived at the same conclusion independently, without knowing the earlier work existed. Dicke was an experimentalist of unusual gifts who had spent the war developing microwave radiometers for radar, and had, without particular fanfare, invented one of the key instruments needed to detect exactly the signal he was now predicting. He set a young colleague, James Peebles, to calculate the expected temperature. Peebles came up with a figure around 10 Kelvin. Dick put 2 more colleagues, Peter Roll and David Wilkinson, to work building a small horn antenna on the roof of the physics building to look for it. They did not know the signal had already been found, 30 miles away, by 2 people who did not want it. At the Bell Telephone Laboratories in Holmdel, New Jersey, Arno Penzias and Robert Wilson had been given the use of a horn antenna built for the early satellite communication experiments. A 15-meter structure of aluminium shaped something like an enormous ear pointed at the sky. Satellite work had moved on, and the instrument was available for radio astronomy, which was what both men actually wanted to do. Before they could measure anything faint, they had to characterize every source of noise in the system, and they were extremely thorough about it. They accounted for the electronics, they accounted for the atmosphere, they accounted for the heat of the antenna structure itself, cooling their reference load with liquid helium to get a clean comparison. And after all of it, a residual hiss remained, about 3.5 Kelvin of excess noise, arriving from every direction equally, unchanged by day or night, unchanged as the Earth turned, unchanged as the seasons went round and the antenna pointed into entirely different parts of the galaxy. They spent the better part of a year trying to get rid of it. They checked every connection. They pointed the horn at New York City to see whether the urban radio environment was leaking in, and it was not. They dismantled and rebuilt the throat of the antenna. They found that a pair of pigeons had nested inside the horn and coated the interior with what Penzias later described, with great delicacy, as a white dielectric substance. They removed the pigeons, cleaned the aluminium, and reassembled everything. The hiss did not change. The pigeons came back and were dealt with less gently the second time, and Wilson later said it was the part of the story he felt worst about. The resolution came through a chain of conversations rather than a flash of insight. Penzias mentioned the problem on the telephone to a radio astronomer named Bernard Burke, who had recently heard about a talk Peebles had given describing the search at Princeton. Burke told Penzias there was a group looking for precisely this. Penzias telephoned Dick. Dick listened to the description of the noise, its temperature, its uniformity, its refusal to vary, put down the phone, turned to the others in the room and said, "Boys, we have been scooped." The 2 groups agreed to publish together. In 1965, 2 papers appeared side by side in the Astrophysical Journal. Penzias and Wilson reported an excess antenna temperature and, in a masterpiece of understatement, declined to interpret it. Dick, Peebles, Roll and Wilkinson explained what it was. Penzias and Wilson received the Nobel Prize in 1978 for a signal they had spent a year attempting to eliminate. Dick did not. Neither did Alpha or Hermann, who had predicted it 17 years before anyone went looking. It was the end of the steady-state model. There is no way to produce a uniform microwave glow at a specific temperature in a universe that has always looked as it does now, Hoyle argued against the interpretation for the rest of his life and never persuaded anyone. The background radiation turns out to be the most perfect black body spectrum ever measured, anywhere, by anyone. A black body is an idealized object that absorbs everything falling on it and radiates purely according to its temperature, and nothing in a laboratory has ever come close to the theoretical curve. The early universe does. When the Cosmic Background Explorer satellite measured the spectrum in 1990, the data points matched the predicted curve. So exactly that, on the published graph, the error bars are smaller than the thickness of the line drawn through them. When the result was shown at a meeting of the American Astronomical Society, the audience stood up and applauded a graph. The temperature today is 2.725 Kelvin. Every cubic meter of space you are sitting in contains roughly 410 million of these photons. They outnumber the atoms of ordinary matter in the universe by more than 1 billion to 1. By count, the cosmos is overwhelmingly ancient light, with a faint residue of matter drifting through it, and we are part of the residue. But the spectrum was only half of what the satellite was built for. The other half was the search for the frozen pattern, the primordial variations that inflation predicted and that had to be there, because without them nothing could ever have collected into anything, and they had proved maddeningly hard to find. Every attempt through the 1970s and 80s had come back with a smooth sky, and the upper limits were getting uncomfortably tight. If the variations had been much smaller still, there would not have been enough time in the history of the universe for gravity to build galaxies out of them. In 1992, the satellite's differential radiometer found them. The variations were about 30 millionths of a degree. Hot and cold patches straying from the average by roughly 1 part in 100,000, distributed across the sky in a pattern statistically consistent with what inflation had predicted. George Smoot, announcing the result, said that if you were religious, it was like looking at God, a remark he immediately regretted and spent years being asked about. John Mather, who had led the spectrum measurement, was more restrained. The two shared the Nobel Prize in 2006. The pattern was there. What came next was reading it. In 2003, the Wilkinson Microwave Anisotropy Probe, named for David Wilkinson, who had built the roof antenna at Princeton and who died the year before the results came out, mapped the same sky at far higher resolution. What matters in these maps is not any individual spot but the statistics, how much variation there is at each angular scale. Plot that and you get a curve with a series of peaks and troughs, and those peaks are not decoration, they are sound. Before the fog cleared, the universe was a plasma, and a plasma carries pressure waves. Gravity pulled matter into the denser regions, radiation pressure pushed back out, and the result was oscillation literal acoustic waves, ringing through the early cosmos at a substantial fraction of the speed of light, at wavelengths measured in tens of thousands of light years. When the fog cleared, the waves stopped dead and their pattern was printed onto the light. The peaks in the power spectrum are the harmonics of that ringing, and their positions and heights encode the composition and geometry of the universe that was doing the ringing. The position of the first peak measures the geometry, because it tells you the true physical size of a feature whose apparent size you can see, and comparing those two things tells you whether light has travelled to you in a straight line or a curved one. The answer is straight. The universe is flat. The second peak measures how much ordinary matter there is, because ordinary matter resists compression differently from anything else. The third measures the dark matter, which participates in the gravity, but not in the pressure. Every peak sat where inflation and the standard model of cosmology said it should. The European Space Agency's Planck satellite, launched in 2009 and reporting its final analysis in 2018, sharpened all of it. The tilt in the fluctuation spectrum, the slight preference for larger variations on larger scales, was measured to be 0.965, with an uncertainty in the fourth decimal place. Inflation had predicted a value slightly below 1, and could not say precisely how far below without knowing the details of the field. It is slightly below 1. The agreement between the observed spectrum and the inflationary prediction is one of the genuine triumphs of the last century of physics, and it is not widely known outside the field because it is a graph rather than a picture. There is a cautionary chapter, and it belongs here. In March of 2014, a team operating a telescope at the South Pole, the second of a series called Background Imaging of Cosmic Extragalactic Polarization, announced that they had detected a particular twisting pattern in the polarization of the ancient light. This pattern cannot be produced by density variations alone. It requires gravitational waves, and gravitational waves of that scale could only have been generated by inflation itself. It would have been a direct measurement of the energy at which inflation occurred, and a direct detection of quantum gravity in action. They held a press conference. A colleague was filmed arriving at André Linde's house with champagne to tell him his theory had been confirmed, and Linde's wife opened the door, and the video went round the world. The signal was dust. The patch of sky they had observed contains grains of silicate and carbon in our own galaxy, aligned by the galactic magnetic field, and aligned dust emits polarized light that mimics the pattern almost exactly. Separating the two requires observing at several frequencies, which their instrument could not do alone. When the Planck team released their dust maps later that year, and the two groups analyzed the data jointly, the entire signal could be accounted for without any primordial component at all. The detection was withdrawn. This was not a scandal, and it was not a failure. The claim was made, the community checked it, the check was decisive, and the claim was retracted inside a year. That is the process functioning exactly as it should. It was, however, a genuinely painful experience for the people involved, who had believed for several months that they had photographed the first instant of time and had told the world so. The search continues with better instruments and more frequencies, and the current limits are tight enough to have ruled out several classes of inflation model already, which is itself progress. Inflation as a framework remains robust. It explains the horizon problem, the flatness problem, and the origin of every structure in the universe, and its statistical predictions have now been confirmed by 3 generations of satellites. What remains open is the mechanism. No particle corresponding to the field has been found, and there is no independent evidence that it exists. Inflation is not one theory, but a large family of them, and we do not know which member is correct, or whether any of them is. The primordial gravitational waves that would settle the energy scale have not been detected. A minority of respected physicists argue the whole framework is unfalsifiable in practice, and should be treated with more suspicion than it receives. But the central claim that the large-scale structure of the cosmos grew from quantum fluctuations stretched by an early episode of exponential expansion is supported by a body of evidence that has survived every test we have been able to devise, and the same ancient light that confirmed it was at the same time delivering a much less welcome message. It was telling us that we had lost most of the universe. The accounting was precise and it did not work. The geometry told us the universe is flat, and flatness is not a vague aesthetic property. It is a quantitative demand. A flat universe requires a total energy density equal to a specific number called the critical density, about 5 hydrogen atoms per cubic meter, averaged across everything, which is a far better vacuum than any laboratory on Earth has ever produced. The ancient light measures the geometry directly, and the geometry says the total must come to 100% of that value. Ordinary matter contributes about 5%. That is everything made of atoms. Every star in every galaxy, every planet, every cloud of gas between them, every grain of dust, every person who has ever lived. The height of the peaks in the sound wave pattern measures the amount of ordinary matter independently of anything else. Because ordinary matter is the only component that both feels gravity and pushes back with pressure, and the answer it gives agrees with the completely independent answer from the abundances of hydrogen and helium produced in the first 3 minutes. 2 different measurements, from 2 different epochs, using entirely different physics. Both say 5%. The other 95 was missing, and the first piece of it had been found more than 30 years earlier by a man almost nobody wanted to work with. Fritz Zwicky was a Bulgarian-born Swiss astronomer who spent most of his career at the California Institute of Technology, where he was regarded with a mixture of awe and exhaustion. He was combative to the point of self-sabotage. He referred to colleagues he disliked as spherical bastards, on the grounds that they were bastards whichever way you looked at them. He was also right about an extraordinary number of things decades before anybody else, including neutron stars, supernovae as a distinct class of explosion, and gravitational lensing as a practical tool. In 1933, he turned his attention to the Coma Cluster, a swarm of something like 1,000 galaxies, about 320 million light-years away. He used the virial theorem, a piece of classical mechanics that relates the average speeds of objects in a gravitationally bound system to the total mass holding them. Measure how fast the galaxies are moving relative to one another, and you can calculate how much mass is required to keep them from dispersing. The galaxies were moving far too fast. At the speed Zwicky measured, the visible mass, the light of all those stars, converted to mass at a reasonable rate, fell short by a factor of several hundred. The cluster should have flown apart long ago. It had not. He concluded that most of the mass in the cluster is something that does not shine, and he gave it a name in German, Dunkel Materie, dark matter. The result was ignored for 40 years. Some of that was his personality, and some of it was legitimate. His distance estimate was too large, and his mass discrepancy correspondingly exaggerated, and the physics of clusters is complicated, and the measurement was hard to check. The idea sat in the literature like a stone in a field. Noticed, walked around, not picked up. Zwicky was not quite the first to use the phrase either. Jacobus Kapteyn, the Dutch astronomer who had spent decades mapping the distribution of stars in our galaxy, wrote in 1922 about the possibility of dark matter in the Milky Way, meaning material that does not shine. And in 1932, Jan Oort in Leiden measured how fast stars in our own neighbourhood oscillate up and down through the plane of the galactic disk as they orbit. That vertical bobbing is governed by how much mass is pulling them back toward the plane, and Oort found more pull than the visible stars could account for. His figure has since been revised, and much of his particular discrepancy turned out to be ordinary gas and faint stars that had simply not been counted. But the method was sound, and the question was in the air a year before Zwicky asked it of a cluster. There is one more thing worth saying about the wind that opened tonight, because it is not merely a poetic framing. It is a specific, calculated quantity. The dark matter halo of the Milky Way is not rotating with the disk. It is a roughly spherical, roughly pressure-supported cloud, and the Sun and its planets are ploughing through it at something like 220 kilometers per second as we orbit the galactic center. From our point of view, that is a headwind, arriving from a fixed direction in the sky, in the constellation Cygnus. And because the Earth's orbit around the Sun is tilted relative to that motion, we move slightly into the wind in June and slightly with it in December, which should produce a small annual variation in the rate at which particles strike a detector a few percent, peaking in early summer. That is a genuinely clever signature, because almost nothing else on Earth varies with that precise period and phase. One experiment beneath the Gran Sasso mountain in Italy has reported exactly such a modulation, at high statistical significance, for more than 20 years. Nobody has been able to reproduce it with any other detector or any other target material, and several experiments built specifically to check it have found nothing. The claim is not withdrawn, and it is not accepted, and it has sat in that condition for 2 decades, which is an uncomfortable place for a result to live. It took a second, cleaner measurement, on a much simpler system, by someone who was not looking for it. Vera Rubin had wanted to be an astronomer since she was a child in Washington, watching the sky through her bedroom window and building a cardboard telescope with her father. When she asked Princeton for a graduate prospectus, she was told the astronomy program did not accept women, which remained true until 1975. She went to Cornell, then Georgetown for her doctorate, which she completed while raising small children, driven to evening classes by her husband because she could not drive. Her master's thesis argued that galaxies might be rotating around some larger center. It was received badly enough that she deliberately chose, for the next stage of her career, a problem so dull that nobody would fight her over it. The problem she chose was measuring how mass is distributed inside spiral galaxies. It seemed like a matter of careful bookkeeping. She worked with Kent Ford, an instrument builder who had developed an image tube spectrograph far more sensitive than anything else available, capable of taking spectra of the faint outer regions of galaxies where earlier instruments saw nothing. The method is straightforward. Take the spectrum of a patch of a galaxy, measure how much its lines are shifted, and you know how fast that patch is moving toward or away from you. Do it at a series of distances from the center, and you have a rotation curve orbital speed plotted against radius. The expected shape was not in doubt. In the solar system, where nearly all the mass sits at the center, Mercury completes an orbit in 88 days, and Neptune takes 165 years. Speed falls off with distance, in a well-defined way that Kepler described and Newton explained. A spiral galaxy looks like the same arrangement, a bright dense bulge in the middle, a disk thinning out toward the edge, so the stars near the rim ought to be moving slowly, their velocities declining as you go outward. Rubin and Ford began with Andromeda, the nearest large spiral, and worked outward from the nucleus. The velocities climbed steeply near the center, exactly as expected. Then they kept measuring, past the bright disk, out into the faint regions where the starlight thins to almost nothing, and there is visibly very little left to provide gravity. The velocities did not fall, they stayed flat. Star after star, in regions where the visible mass had clearly run out, the orbital speeds remained as high as they had been near the center. She checked it. She and Ford measured more galaxies, eventually more than 60 of them, spirals of every size and orientation. The curves stayed flat, every single time. Whatever was holding those outer stars in their orbits was massive. It extended far beyond anything the telescope could see, and it did not emit light. Rubin presented the results without drama, which was deliberate. She understood that a woman making a claim that overturned the mass budget of the universe would be examined more harshly than a man making the same claim, and she let the curves do the arguing. There were 60 of them, and they all said the same thing. Within a decade, the field had accepted it. If Newton's law of gravity is correct, and it has passed every test from the laboratory bench to the outer planets, then every spiral galaxy sits inside a roughly spherical halo of invisible material, extending perhaps 10 times farther than the visible stars and containing something like 5 to 10 times as much mass. Dark matter is not a correction to the picture of a galaxy. It is the galaxy. The luminous part is a bright smear near the middle of something much larger. 2 independent lines of evidence agreeing is good. A third, using entirely different physics, is better. Mass curves space-time, and curved space-time bends the path of light. This is not a hypothesis. It was the first confirmed prediction of general relativity measured during the eclipse of 1919. When a massive object sits between us and a more distant light source, the image of the distant object is distorted, smeared into arcs, or multiplied into several copies, or magnified. The degree of distortion depends only on the mass and its arrangement, and not at all on whether that mass emits light. Photograph a cluster of galaxies, measure the distortion of everything behind it, and you can weigh the cluster without caring what it is made of. Every such measurement finds the same shortfall Zwicky found. The most direct demonstration came in 2006 from a pair of galaxy clusters that had collided head-on roughly 150 million years earlier, known as the bullet cluster because of the shape of the shockwave. Consider what happens in such a collision. The galaxies themselves are mostly empty space and pass through one another almost without interacting. Direct stellar collisions are essentially non-existent, but the hot gas filling the space between the galaxies, which holds most of the ordinary matter in a cluster, several times more than all the stars combined, cannot pass through itself. It slams together, heats to tens of millions of degrees, and stops in the middle, glowing in X-rays that an orbiting telescope can map precisely. So there are 2 things to locate. Where is the ordinary matter? In the middle, in the shocked gas. Where is the total mass? That is measured separately by gravitational lensing of the galaxies behind. They are not in the same place. The mass is not in the middle with the gas. It is out on either side, travelling with the galaxies, having sailed straight through the collision as though nothing had happened. 2 clouds of something that carries the great majority of the mass, does not slow down, does not shock, does not heat, does not shine, and does not appear to notice that another cloud of itself has just passed through it at several thousand kilometers per second. This is the observation that is hardest to explain any other way, and it is why it is cited so often. Modifying the law of gravity can reproduce flat rotation curves, an idea called modified Newtonian dynamics, proposed by Mordechai Milgrom in 1983, does exactly that with one adjustable parameter, and does it impressively well for individual galaxies. But modified gravity puts the gravitational effect where the visible matter is, and in the bullet cluster the visible matter is in the middle and the gravity is not. There is a 4th line from an entirely different direction, and it may be the most persuasive of all. Since the late 20th century, cosmologists have run simulations of structure formation. You begin with the actual measured fluctuations from the ancient light, apply the known laws of gravity, and let a computer evolve the whole thing for 13 billion years. Then you compare the result to the sky, Run it with only ordinary matter, and it fails completely. Before the fog cleared, ordinary matter was coupled to the radiation, and radiation pressure smoothed out any clumping as fast as gravity produced it. There is simply not enough time afterwards to build galaxies. The simulation returns a bland, structureless universe with nothing in it. Add dark matter cold, meaning slow-moving, and collisionless, meaning it interacts only through gravity and the simulation comes alive. The dark matter, feeling no radiation pressure, begins clumping long before the fog clears, building a scaffold of filaments and knots. When the ordinary matter is finally released, it falls into wells that are already waiting for it, and it has a head start of hundreds of thousands of years. Galaxies form on schedule, and the pattern the simulation produces a web of filaments meeting at dense nodes with vast near-empty voids between them. Threaded across billions of light years is the pattern that galaxy surveys actually find when they map the real sky. The cosmic web is a map of where the dark matter went. The galaxies are decoration on it. By the time the final analysis was published in 2018, the numbers were tight. Dark matter is about 27% of the total energy density of the universe. Ordinary matter is about 5%, which means that of all the matter there is, roughly 85% of it is dark. It is the dominant material substance in the cosmos by a wide margin, and everything we have ever touched or seen or built is the minority component, and we do not know what it is. This is not for lack of effort, and the scale of the effort is worth appreciating. For 30 years, physicists have built detectors in deep underground laboratories, in disused mines, under mountains, beneath kilometers of rock that filters out the constant rain of cosmic radiation that would otherwise swamp any signal. Inside, they place tanks of ultra-pure liquid xenon, or crystals of germanium, cooled and shielded and monitored, and they wait for a single dark matter particle to happen to strike a single atomic nucleus and produce a recoil of a few thousand electron volts. The favoured candidate for decades was a class of hypothetical particle predicted by extensions of the standard model of particle physics massive, but interacting only through the weak nuclear force and gravity, which would make it almost perfectly transparent to ordinary matter while still being produced in the right abundance in the early universe. The coincidence between the predicted abundance and the observed one was striking enough to have its own name. It looked like the answer. The Large Underground Xenon Experiment in South Dakota, its larger successor, the multi-ton xenon detector beneath the Gran Sasso mountain in Italy, and the Panda X experiment in a tunnel in Sichuan have between them improved sensitivity by more than 5 orders of magnitude. They have seen nothing. The searches have now excluded most of the parameter space where the favoured candidate was expected to live and are approaching the point where the background rain of neutrinos from the Sun will make further improvement extraordinarily difficult. Attention has partly shifted to Axion's hypothetical particles far lighter, proposed originally to solve an unrelated puzzle about why the strong nuclear force does not violate a symmetry that it is permitted to violate. If they exist in the right mass range, they would also be a fine dark matter candidate, and experiments using strong magnetic fields and finely tuned microwave cavities are searching for them. No confirmed signal, sterile neutrinos, primordial black holes, and various modifications of gravity remain on the table. None has been confirmed. We can map it. We can weigh it. We can watch it pass through the wreckage of colliding clusters like a ghost through a wall. We can prove it was here before the first star, and that nothing we see would exist without it. We cannot say what it is. Billions of these particles are passing through your body as you listen to this. They are not stopping. They do not interact with your atoms in any way that leaves a record. They built the scaffold inside which the Milky Way assembled, and without them there would be no galaxy, no sun, no earth, and no iron in your blood to notice any of it. Something is in the room, and in you, and we cannot name it. Even with all of it in the ledger, the accounts were still badly short. Ordinary matter and dark matter together came to about 32%. The flat geometry demanded 100. The remaining 68% was something that did not clump at all, that formed no halos, built no filaments, and left no trace in the rotation of any galaxy. It would not be found by looking at how things gather. It would be found by looking at how everything comes apart. The discovery began with a question that everybody assumed had a boring answer. How fast is the expansion of the universe slowing down? By the early 1990s, the expansion itself was beyond dispute. What remained was to measure the rate at which gravity was putting the brakes on. Every galaxy, every atom, every particle of dark matter pulls on everything else. That pull acts against the expansion. It must. There was no serious alternative on the table, and the only open question was the magnitude, because the magnitude determines the ending. If the density of matter were high enough, gravity would eventually halt the expansion and reverse it, and everything would fall back together into a big crunch. If the density were lower, expansion would continue forever, coasting, decelerating without ever quite stopping. Either way, deceleration. The number describing it even had a name, the deceleration parameter, and it was written with a sign convention that assumed it would come out positive, because of course it would. Measuring it requires comparing the expansion rate now with the expansion rate long ago, which means measuring distances to objects billions of light years away with real precision. Ordinary galaxies are useless for this. They come in every size, and there is no way to know how bright one ought to be. What is needed is a standard candle, a class of object whose true brightness is known, so that its apparent brightness gives its distance directly. It is Henrietta Leavitt's method again, applied at 100 times the range, because Cepheid variables become impossible to pick out long before you reach the distances that matter here. The candle that worked was a particular kind of exploding star. A Type 1a supernova happens when a white dwarf, the exposed, dead core of a star like the Sun, a body roughly the size of the Earth containing roughly the mass of the Sun, held up not by heat but by the resistance of tightly packed electrons, gains mass from a companion star. As it gains, the pressure at its center rises, and there is a hard limit to how much it can bear. That limit was calculated in 1930 by a 19-year-old named Subramanian Chandrasekhar on the ship carrying him from India to England, and it works out to about 1.4 times the mass of the Sun. Beyond it, the electron resistance fails, the core collapses, carbon fusion ignites across the whole object in a few seconds, and the star is destroyed entirely in an explosion that briefly outshines the galaxy containing it. Because the trigger is always the same mass, the explosions are nearly identical. Not perfectly, but the differences are systematic and correctable. Supernovae that fade more slowly are intrinsically brighter, in a tight relationship discovered by the Ukrainian astronomer Yuri Pskovsky and refined by Mark Phillips in the early 1990s. Measure the shape of the light curve, apply the correction, and you know how bright the explosion really was to within a few percent. Compare that to how bright it looks, and you have a distance. Take the spectrum of the host galaxy, and you have a redshift. Enough of those, spread across a range of redshifts, and you can reconstruct the history of the expansion. The practical difficulty is that these events are rare, perhaps one per galaxy per century and unpredictable, and they fade within weeks. Finding them at cosmological distances requires imaging enormous numbers of galaxies repeatedly, and comparing the images to catch what has changed, then getting a large telescope pointed at the right spot within days. In the era before wide-field digital detectors, this was close to impossible. That is why the measurement waited until the 1990s. Two teams took it on, and their rivalry was real. The Supernova Cosmology Project, based at the Lawrence Berkeley National Laboratory, was led by Saul Perlmutter and had been working on the problem since the late 1980s. They had solved the scheduling problem with a technique they called the batch approach. Observe an enormous field just after a new moon. Observe it again just before the next one. Compare the images and reliably produce a handful of new supernovae on a predictable date, so that follow-up telescope time could be booked in advance rather than begged for. The High Redshift Supernova Search Team formed in 1994, led by Brian Schmidt, then 27 and working in Australia, with Adam Rees doing much of the analysis, and Nicholas Suntsev and Robert Kirshner also central to it. They were mostly supernova specialists who thought the Berkeley team, who were mostly particle physicists, were underestimating how badly the explosions vary and how much dust could distort the result. Both teams expected to measure a deceleration. Both wanted to be first. The data did not make sense. The distant supernovae were too faint, around 25% fainter than they should have been. A supernova that appears fainter than expected is farther away than expected. which means the universe has expanded more since that light left than a decelerating model allows. There is no way to arrange that with gravity alone. Rias, doing the analysis for the high redshift team in the autumn of 1997, assumed he had made a mistake and spent months trying to find it. Dust in the host galaxies could dim a supernova, but dust also reddens, and the colours showed no such reddening. Perhaps distant supernovae are intrinsically different from nearby ones, because the early universe had fewer heavy elements, but the spectra of the distant events matched the nearby ones closely. Perhaps the selection was biased toward finding only the brightest examples at great distance. The effect was quantified and it was too small. He wrote to a colleague that the result was making him crazy and that the data required a universe with a negative deceleration. Perlmutter's team, using different search strategies, different reduction software, and different assumptions, was converging on exactly the same answer. Both teams announced within months of each other, and the papers appeared in 1998 and 1999. The expansion of the universe is not slowing down, it is speeding up. It took years for the field to fully absorb it, and the initial reaction from many was that one of the two teams must be wrong, until it became clear that the only way to make both wrong was to make them wrong in identical ways for different reasons. Something is pushing outward, overcoming the combined gravitational attraction of every particle of matter in the cosmos, and driving the galaxies apart at an accelerating rate. The simplest description of that something is a term that had been sitting discarded for 80 years. Einstein's cosmological constant, the patch he added in 1917 to hold the universe still and then abandoned, as an embarrassment describes exactly this. An energy density belonging to space itself, the same everywhere, which does not thin out as space expands, because there is simply more space, and therefore more of it. Its pressure is negative, so its gravity pushes rather than pulls. As matter dilutes and this does not, it inevitably comes to dominate, and once it dominates, the expansion accelerates forever. Perlmutter, Schmidt, and Rees shared the Nobel Prize in 2011. Einstein's greatest blunder turned out to be his second most important contribution to cosmology, and it now runs the universe. The final accounting from the Planck analysis in 2018 reads as follows. Dark energy, 68.3% of the total. Dark matter, 26.8%. Ordinary matter, everything made of atoms, everything in every telescope image ever taken, everything anyone has ever held, 4.9%. The dark sector makes up about 95% of reality. The visible universe is a rounding error that happens to contain us. And the largest component is the one we understand least. That statement needs a number attached, because the number is not merely large, it is the worst in the history of physics. Quantum field theory predicts that the vacuum should have an energy density. Everything in this script has been building on the fact that it does. The trouble is calculating how much. Add up the 0-point energy of all the fields, cutting the sum off at the scale where quantum gravity takes over, and you get a value that exceeds the measured dark energy density by roughly a factor of 10 to the 120. That is a 1 followed by 120 zeros. It is not close. It is the largest disagreement between theory and observation anywhere in science, and it has been sitting there, unresolved, since the 1960s. Physicists call it the cosmological constant problem, and its existence is a standing reminder that the vacuum, which is the foundation of the entire argument we have been building tonight, is not fully understood by anyone. There is a further smaller puzzle sitting alongside it, and it has been getting sharper rather than softer. Measure the current expansion rate using nearby standard candles, working outward from Cepheids to supernovae, and you get about 73 kilometers per second per megaparsec. Infer the same quantity from the ancient light, using the standard model to run the calculation forward from the early universe, and you get about 67. Both measurements have been refined for 2 decades, and the error bars have shrunk while the gap has not. This is called the Hubble tension, and either one of the measurements has a systematic error nobody has found, or something in the standard picture between the fog clearing and now is missing. It is unresolved. Anyone who tells you it is settled is telling you their preference. There is a real question about whether dark energy is the cosmological constant at all, and it is being actively pursued rather than assumed. A constant has a very specific signature. Its density never changes, anywhere, forever as the universe grows. The alternative is that it is a field, slowly evolving, whose density drifts over cosmic time. That family of models goes under the name quintessence, after the classical fifth element, and it makes a testable prediction. The strength of the push should not be quite the same at every epoch. The quantity being measured is the relationship between the pressure of dark energy and its density. For a true cosmological constant, that ratio is exactly -1, and nothing will ever shift it. If it is even slightly different, or if it has changed since the light left the distant supernovae, then dark energy is dynamic, and the future is a different future. Every measurement so far has come back consistent with -1, which is the boring answer and probably the correct one. But the error bars are wide enough that a small deviation would still be hiding inside them, and recent results from large galaxy surveys have produced hints, not detections, hints that the value may have drifted. If that survives further data, it would be the most significant development in cosmology since 1998. If it does not survive, it will join a long list of 2 sigma excitements that evaporated, which is where most such hints go. The difference matters for how everything ends. If the ratio is exactly -1, the universe expands forever, cooling, emptying, running down over timescales beyond arithmetic. If it is even slightly more negative than -1, a scenario called phantom dark energy, the push strengthens without limit, and the expansion eventually overwhelms gravity at every scale, in sequence. Clusters unbind, then galaxies, then solar systems, then planets, then atoms, in a final interval of a few tens of millions of years. That ending has a name, the Big Rip, and it is not favoured by the data, but it is not excluded either. If the acceleration is real and permanent, the future has a shape, and it is worth being precise about it. Galaxies not bound to us by gravity will recede faster and faster. Eventually their recession will exceed the speed of light which relativity permits. Because they are not moving through space, space is growing between us, and their light will never reach us again. They will cross a horizon and go out, one by one, not by moving anywhere, but because the gap becomes uncrossable. Our own local group, gravitationally bound, will not disperse. The Milky Way and Andromeda will collide in about 4 billion years and merge into a single elliptical galaxy. That merged object, with its handful of small companions, will remain. Everything else will leave, and the ancient light will go with it. As space expands, those photons stretch further, their temperature falling toward absolute zero, until their wavelengths exceed anything any detector could resolve. The evidence that the universe had a beginning will be erased by the same expansion that revealed it. That is not a consequence anyone predicted when the acceleration was discovered, and it has a strange implication for what it means to know something. We will come back to it. First, there is a question left standing from the beginning of the night, and it is the one the whole argument turns on. We have established that the vacuum is not empty and that a universe can cost nothing, but every vacuum we have discussed exists inside space and time and obeys laws that were already there. What about before that? What about nothing at all? The pieces are on the table now, so let us set them out before assembling them. The vacuum is not empty, and this is not a theoretical claim. It shifts the energy levels of hydrogen and it pushes metal plates together, and both effects have been measured. A universe can, in principle, carry a total energy of 0 because the positive energy of matter is offset by the negative energy of gravity, and a zero energy fluctuation has no debt to repay and no deadline. A speck of spacetime can become a cosmos because exponential expansion driven by a trapped field will do exactly that. And the fingerprint of that episode is printed on the oldest light in a pattern we have now measured to 4 decimal places. The structure of everything, from the largest filaments down to the arrangement of stars in the sky, began as quantum noise. That is a chain of reasoning with observational support at almost every link. What it does not yet do is answer Leibniz, because at every step there was already something there. Leibniz asked why there is something rather than nothing, and the force of the question comes from an assumption buried so deep in it that it is easy to miss. He assumed that nothing is the default. Leibniz. That absence is what you get when nothing happens, and that presence is the thing requiring explanation. Under that assumption, the argument is close to unanswerable. because you can always ask what tipped the scales. The physics of the last century has undermined the assumption rather than the argument. Nothing, in every sense we have been able to examine, is not calm and is not featureless and is not a state that persists. But the vacuum we can probe in a laboratory is still not the deepest kind of nothing, and it would be dishonest to pretend otherwise. That vacuum sits inside spacetime. It has a geometry. It obeys quantum field theory and general relativity. It is the lowest state of a system, and a system is a something. So the question can be pushed one level further down, and it should be. What about the absence of spacetime itself? A state with no dimensions, no fields, no duration, nothing to be low in. For most of history, that was a question for philosophers, because there was no mathematics that could describe such a state, or the transition out of it. In 1982, that changed. Alexander Vilenkin at Tufts University published a short paper titled Creation of Universes from Nothing, and he meant the word literally, which he was careful to spell out. Not a pre-existing vacuum, not an empty region of space, a state with no space, no time, no matter, no energy, and no geometry of any kind. His mechanism was quantum tunneling, which is not exotic, it is one of the most thoroughly confirmed effects in physics. A particle confined behind a barrier it lacks the energy to climb has a calculable probability of simply appearing on the far side. It does not go over, and it does not go through. The wave function describing it has a small amplitude beyond the barrier, so there is a small chance of finding it there. This is not a curiosity. It is why the sun shines, because the protons in its core do not have enough energy to overcome their mutual repulsion and fuse anyway. It is how the tunneling microscope works. It is why, some atomic nuclei decay. Vilenkin's insight was that the same formalism can be applied to the geometry of a universe rather than to a particle in a box. In the equations describing a closed universe, there is a barrier between a state of zero size and a state of finite size, a classically forbidden region that the universe cannot cross by expanding, because to expand it would have to pass through configurations it is not permitted to occupy. It can tunnel, and what emerges is a tiny closed bubble of space-time, of a definite calculable size, filled with a false vacuum energy that immediately drives inflation, which then produces everything else. The total energy of that bubble is exactly zero, because it is closed, which is the one case where the accounting is unambiguous. It borrows nothing, because there is nowhere to borrow from. This is not proven, and Vilenkin has never claimed otherwise. It rests on combining quantum mechanics with general relativity in a regime where we know that combination is incomplete, and a real answer requires a theory of quantum gravity that we do not have. But it is not speculation of the loose kind. It is a mathematical model, published in a peer-reviewed journal, which demonstrates something with genuine philosophical weight, that a universe emerging from literally nothing is not logically incoherent and not physically forbidden. The equations describe the transition. They do not describe a cause, because the transition does not happen in time. Time is part of what appears. There is no before in which anything could have acted, and the question what caused it may simply not have a referent, in the same way that asking what is north of the North Pole does not. At almost the same moment, working independently, James Hartle and Stephen Hawking developed a different picture, with a similar destination. Their question was what the quantum state of the entire universe should look like. In ordinary quantum mechanics, you specify a state at some initial time and evolve it, but there is no outside clock for the universe as a whole and no external time to evolve against, so the usual procedure has nothing to stand on. Hartle and Hawking proposed that the universe be described by a sum over every possible history it could have had, the standard method for calculating quantum amplitudes, applied to geometry itself with one condition. The histories included in the sum have no initial boundary, no edge, no first moment at which conditions had to be specified by anything outside. To make that work mathematically, the time coordinate near the beginning is treated as imaginary, in the technical sense of involving the square root of -1, which converts time into a fourth spatial dimension. The effect on the geometry is to replace the sharp singular point of the Big Bang with something smooth and rounded, and the analogy Hawking used for the rest of his life is the South Pole. Stand at the South Pole, there is no edge. There is no point at which the Earth stops and something else begins. The lines of longitude converge there, so it is a special point on any map, but it is not special on the surface. It is ordinary ground, exactly like the ground 100 meters away. And asking what is south of it is not a hard question awaiting a clever answer. It is a question whose terms stop applying. In the no-boundary proposal, the beginning of the universe is like that. Finite, self-contained, with no edge and no moment of creation. Not a universe that began, but a universe that is. Hawking put the consequence bluntly in A Brief History of Time. So long as the universe had a beginning, we could suppose it had a creator. But if it is really completely self-contained, having no boundary or edge, it would have neither beginning nor end. It would simply be, what place then for a creator? That is a strong statement, and it has been strongly contested, and not only by theologians. The most serious objection is a philosophical one, and it is worth taking seriously, because the honest version of tonight's argument has to survive it. Both models assume the laws of physics. Vilenkin's tunneling requires quantum mechanics to be true before there is a universe for it to be true of. The no-boundary proposal requires a formalism for summing over geometries. The laws are not nothing. They are a mathematical structure, a set of rules governing how fields behave and how probabilities are assigned. And if you invoke them to explain why there is something, you have not explained why there are laws. The philosopher David Albert put this as sharply as anyone in a review of Lawrence Krauss's book A Universe from Nothing in 2012. Krauss had argued that the universe could arise from a quantum vacuum and had used the word nothing for that vacuum. Albert pointed out that a relativistic quantum vacuum, with its fields and its background space-time, is not nothing in any sense a philosopher would recognize. It is a physical system with properties. Calling it nothing does not answer Leibniz's question. It relabels it. The review was scathing, and the exchange that followed was less than dignified on both sides. But the point stands, and Krauss's response did not fully dispose of it. Krauss's reply was that the philosophical notion of absolute nothing may be a category with no application, that it is a word we constructed by taking away every property we could think of, without ever checking whether the result describes anything possible. And there is a version of this that is more than defensive. In some approaches to quantum gravity, the laws we observe are not fundamental at all, but emergent, in the way that the laws of thermodynamics emerge from the statistics of atoms without being extra rules imposed on top. If that is right, then the deepest level might be a mathematical structure rather than a set of commandments. And asking why these laws would be like asking why the number 7 is prime. Nobody knows. It may not be knowable, because we cannot run an experiment on the absence of everything, and there is no obvious way to get evidence about it. But notice what has happened to the original argument even so. Leibniz's case for a necessary being depends entirely on the premise that nothing is the default state, that if there were no God, there would be an eternal void, and the appearance of a universe therefore demands an intervention. That premise is not a conclusion he reached, it is an assumption he inherited, along with a static, eternal, unchanging cosmos, and a vacuum that was simply an absence of stuff. Every part of that picture is now known to be wrong. The vacuum is a physical system that fluctuates and pushes and cannot be switched off. The universe is not static, and has a finite past. The energy books balance at zero, so no fortune had to be provided. There is a mechanism by which space-time can begin without a prior moment. And in every formulation that science has been able to examine, nothing is unstable. It seethes. It fluctuates. It produces particles and fields, and, if the mathematics is being read correctly, universes. You do not need someone to light the match, because the match lights itself, and always would have. That is not a proof that God does not exist, and I want to be exact about that because the difference matters. Physics does not deal in proofs about the supernatural and cannot. What it does is remove the necessity. The oldest and most durable argument for a creator turns out to rest on a misunderstanding of what nothing is, an understandable one, held by brilliant people for 3,000 years, and wrong. When you examine nothing closely, with quantum field theory and general relativity and the mathematics of tunneling, you do not find a void waiting to be filled. You find a structure with a built-in tendency to become something. And if it happened once, there is no obvious reason it happened only once. This is where the physics runs past the evidence. and it should be labelled as such. In eternal inflation, a consequence of the standard models rather than an addition to them, the field-driving expansion never decays everywhere at the same time. It decays here and there, in patches, and each patch becomes a universe with its own hot beginning. Meanwhile, the space between the patches goes on inflating, faster than the patches can consume it, producing new regions forever. Our entire observable cosmos would be one bubble among an unbounded number, each with its own history and possibly its own physical constants. This is not confirmed. It may not be confirmable, since the other bubbles are permanently beyond any horizon we could reach. Some physicists regard it as the natural extension of a well-supported theory, and some regard it as the point where cosmology stops being science, and both camps contain people worth listening to. But if it is right, it changes the tone of the answer. Not merely that something can come from nothing, that it does endlessly, and that the question why is there something rather than nothing has the same status as asking why there is weather. And if that is what the universe is, one more question follows, and it is the one that has stayed with me longest. What will the last observers see? Lie back, let the dark settle. The particles are still moving through you. Now cast your mind forward, not 1,000 years and not 1,000,000. 100 billion years from this quiet hour, an interval about 7 times the entire age of the universe so far, which means that everything that has happened, from the fog clearing to this moment, is a short introductory passage compared to what follows. The expansion that Slipher measured on cold nights in Arizona, and the acceleration that 2 rival teams stumbled into in the 1990s, will have finished their work. Every galaxy not gravitationally bound to our own will have receded beyond the horizon, not moved away, receded, carried off by the growth of the space between, at a rate that eventually exceeds the speed at which light can close the gap. Their light will not be dim. It will not arrive at all. There is no instrument that can be built at any level of technology that can retrieve a signal from beyond that boundary, because the boundary is not a matter of sensitivity, it is a matter of causal structure. What remains will be a single galaxy. The Milky Way and Andromeda will have collided and merged, along with the Triangulum Galaxy and the several dozen dwarf companions of the local group, into one large elliptical mass of stars, an object astronomers have already given a provisional name, Milkomeda, which is not a good name, but is the one we have. It will sit alone in a darkness, with no far side. An observer on a world orbiting a star in that galaxy will look up at a night sky containing stars, and beyond the stars, nothing. No other islands of light, no cosmic web, no smudges of distant spirals to argue about. The sky will look, to a reasonable and careful observer, exactly like a finite collection of stars in an infinite and empty void. The ancient light will go too. Those photons, which have been travelling since the fog cleared and which carry the entire record of the beginning, will have been stretched until their wavelengths exceed anything that can be measured. Their temperature will have fallen to a small fraction of a billionth of a degree above absolute zero. They will still be there in some technical sense, and they will be undetectable in every practical one, lost beneath the noise floor of any conceivable instrument. The abundances will fail as evidence too. The primordial ratio of hydrogen to helium, which is one of the strongest pillars we have, will have been overwritten by 100 billion years of stellar processing. Generations of stars will have fused and scattered and fused again, until the composition of the gas records nothing but the history of that one galaxy. And this was worked out, carefully and quantitatively, in a paper published in 2007 by Lawrence Krauss and Robert Scherer, with the title, The Return of a Static Universe and the End of Cosmology. It is not a thought experiment. It is a calculation of what a scientist in the far future would actually be able to measure. So imagine them. They will be curious, because curiosity is what observers are for. They will build telescopes, and the telescopes will work, and they will point them at the sky and see only their own galaxy, spread across every direction, with darkness beyond it. They will measure the motions of the stars within that galaxy and find them consistent with a stable, bound, gravitationally sensible system, rotating quietly, going nowhere in particular. There will be dark matter in their measurements, holding the whole thing together, and they will presumably notice that as we did. But there will be no expansion to detect, because nothing observable will be receding. There will be no afterglow, because it will have gone under the noise. There will be no distant galaxies whose redshifts could be plotted against distance, because there will be no distant galaxies. They will ask exactly the questions we ask. How old is this? How did it begin? What is its fate? And they will do what we did, look for evidence. There will be none, if they are rigorous, and there is no reason to assume they will be less rigorous than we are. They will conclude that the universe is eternal and static, a single island of stars, existing indefinitely, with no beginning to explain and no history to reconstruct. They will arrive, by honest reasoning from complete evidence, at precisely the cosmology that Einstein assumed in 1917 and that Hoyle defended into the 1990s, and they will be wrong, and there will be no way for them to find out. This is the part I find hardest to put down, not because it is sad, though it is a little sad, because of what it says about the relationship between evidence and truth. We have spent this entire night building an argument out of observations, the shift in hydrogen's energy levels, the force between two plates, the redshifts of spiral nebulae, the flat rotation curves, the faintness of distant supernovae, the ripples in the ancient light measured to 4 decimal places. Every step was anchored to something somebody measured. That is the whole strength of the case, and it is what separates it from Leibniz reasoning in a study in 1714. But the evidence is not permanent, it has a shelf life. It was laid down at the beginning and it is being erased continuously, and the window during which it can be read is a few tens of billions of years out of a future that runs to numbers with no names. We are inside that window, not because we deserve to be, and not because anything arranged it, but because the same expansion that will eventually erase the record has not yet finished doing so. We are late enough that generations of stars have manufactured the carbon and oxygen and iron required to make an observer, and early enough that the light from the beginning is still arriving. Those two conditions overlap, and we are in the overlap. We are the generation that gets to know. The ones who come after, in the long dark energy-dominated stretch, will be stranded in a void with an honest, careful, thoroughly evidenced picture of the universe that happens to be false in nearly every particular. Return, now, to the room where this began. The darkness is the same darkness. The unseen wind is the same wind. Roughly 85% of all the matter in the universe is still invisible, and it is still passing through your body. Billions of particles every second, leaving no trace of any kind. We can map it. We can weigh it. We can watch it sail through the wreckage of 2 colliding clusters without slowing. We still cannot say what it is. It built the scaffold inside which every galaxy formed, including the one that made the iron in your blood and the calcium in your bones. And it is in the room now, moving through the walls and the bed and you, asking nothing, requiring nothing, entirely indifferent to whether anyone is here to notice. Beside it, larger still, is the dark energy 68% of everything, pushing outward, patient, and eventually responsible for emptying the sky. And beneath both of those, older than both, is the fact we started with and have to come back to. Absolute nothingness, the true void, the calm and featureless absence that Leibniz imagined as the only alternative to a created world is not a stable state. It has energy. It fluctuates. It shifts the levels of a hydrogen atom and shoves 2 metal plates together and, if the mathematics is being read correctly, it tunnels into universes. The simplest explanation for why God does not exist is that a creator was never needed. Not because the universe is a lucky accident, and not because the question was foolish. It was an excellent question, asked by a serious man, and it lasted 3 centuries because it deserved to. But it contained an assumption about emptiness that turned out to be false, and when the assumption fell, the necessity went with it. Nothing is not an absence. It is a condition that cannot hold. The universe exists because it could not remain empty. The particles pass through you without sensation. The ancient light is still arriving, from a fog that cleared before there was an Earth to arrive at, and it will keep arriving for a while yet. The equations balance to 0,